day. Now we're going to discuss about the deformation of the Earth, the plate boundaries, the tectonic plates, and the evidence Alfred Wegener once created, and the theory that he proved that Earth as one gigantic continent called Pangea. Now my good friend will tell you about the deformation.
We understand that changes in the Earth are the result of natural processes.
The Earth is changing?
From our perspective, the Earth's surface may seem stationary and rock steady, but we know that it's always in motion and has gone through big changes over time.
How do we know that?
By observing earthquakes, volcanoes, and other seismic activity, scientists have developed theories to explain the movement and deformation of the Earth's crust over millions of years. In this issue, we'll see how the face of our planet has been changed by volcanic eruptions and colliding continents.
Inelastic deformation has two kinds, the ductile deformation and the brittle deformation. Ductile and brittle. So, ductile deformation is similar to a modeling clay because once you mold a clay, it will not go back to its original ball state. While the brittle deformation is similar on how a piece of biscuit breaks into pieces. So, under ductile deformation, faults are the best evidences. And one of its examples is the orogeny. I will spell it out. O-R-O-G-E-N-Y. So, orogeny is a process of mountain building that usually associated with a compressive stress. While in brittle deformation, one of its examples is the faults having a break on the rocks and the surface.
Now we're going to proceed to the deformation of the crust. Historically, this has already been observed by a scientist named Alfred Wegener in 1912. He wrote a book about the origin of continents and oceans. In his book, it stated in his book that continents were actually connected to each other. The theory was supported by different evidences. Later on, this theory is called continental drift theory, where Alfred Wegener expanded it into what we know as plate tectonics. Plate tectonics. This theory is supported by four evidences. The first one is the jigsaw puzzle. Jigsaw puzzle. The second one is the terrestrial fossils. The third one is the similar and structures. Similar and structures. And lastly, the ancient climbing. The first evidence is about the jigsaw puzzle. Its example is the world map, where you can see all the continents are shaped like jigsaw puzzles that you could fit to each other. Like the South America and Africa, where you could fit its continents to each other. Now the second theory is about terrestrial fossils. This evidence is where the fossils is used to determine that two continents are connected to each other. It's like the fossils of the Mesosaurus, where they found its remaining parts between South America and Africa. The third theory is about rock and structures. This is about rock and structures, where its coastlines are alike to each other. The coastlines between Brazil and Africa, British Isles, and Scandinavia. The fourth evidence is Asian climbing. It is going back to our previous statement on terrestrial fossils. The presence of glossopteris in Antarctica raised a big question. Why is it their polar region? The answer can be found in the continents of South America and Africa, Australia, and Eurasia. It is the ancient glacier deposits of around 300 million years old cover the southern coastlines of these continents. We're going to proceed to plate tectonics. Plate tectonics present the evidence that land masses move and were once joined together. This theory, however, is not able to present a mechanism for the movement with the advent more sophisticated and advanced tools for geologic exploration data from the bottom of the ocean became available. Now we're going to the next, the plate boundaries. Do you know what the plate boundaries is? Plate boundaries. The motional lithosphere portion of the Earth's crust independently from each other as one unit. These units are what we call lithospheric or tectonic plates. Tectonic plates range in size from small units or microplates to big ones. This tectonic range ranges in size from small. 7 major lithospheric plates account for more than 90% of the Earth's surface: North America, South American, Pacific, African, Eurasian, Australian, Indian, and Antarctic plates. It should be noted that lithospheric plates do not necessarily mean the land masses that they present. Lithospheric plates include the oceanic crust that goes beyond the coastlines of continents until a tectonic plate boundary is reached. Several smaller tectonic plates include Caribbean, Nazca, Philippines, Arabian, Cocos, Scotia, and Juan de Fuca plates. Along with the bigger tectonic plates, these intermediate plates contribute to the total surface area of the Earth. Now, this tectonic plates is divided into 3 types: the divergent, convergent, and transform boundaries. Divergent boundaries, also known as constructive margins. Divergent boundaries define areas where plates move apart. Because of this movement, new material is introduced under the surface of the new oceanic crust material. While in convergent boundaries, plates collide with each other in convergent boundaries. Because of this collision, one plate usually subducts or goes under the other plate, which is usually density driven. In effect, one plate goes back into the mantle, and the other plate goes back into the crust. Additional materials will cause significant change in the mantle, can form in volcanic chains or mountain ridges. And lastly, transform wall, where 2 plates neither collide nor move away. Plates simply slide past to each other without the creation or destruction of lithosphere.
1912, German geophysicist Alfred Wegener proposed the idea of continental drift. He stated that the continents were not fixed, but instead were moving. While at the time he wasn't entirely sure how or why this happened, we now understand tectonic plates causes this over an incredibly long period of time. For most of Earth's history, continents have joined together, split apart, and smashed back together. Our modern-day world is just a snapshot. Earth has always been changing, in a process going back thousands of millions of years. At different periods of Earth's history, the continents would sometimes clash together, forming a landmass known as a supercontinent. Like Pangaea, you're probably thinking. Yes, exactly. Pangaea, however, was not the first supercontinent. Before Pangaea, there were ancient continents of the Precambrian globe, a time spanning billions of years before multicellular life even developed. The formation of these supercontinents greatly influenced modern geography, which in turn influenced modern civilization. So let's take a look at these continents of the past. Valbara. While only a theory as of now, the continent of Valbara is theorized to have been the very first continent. Forming around 3.6 billion years ago, a billion years after the formation of Earth, it was a supercontinent for the time, since it was, well, the only continent. Since it's so far back, very little is known about this theorized landmass. It's believed to have consisted of parts of South Africa, Botswana, Zimbabwe, and a small mass in northwest Australia. Ur is the oldest confirmed continent in Earth's history. At the time, 3 billion years ago, it was the largest continent on the planet because just like Valbara, it was the only one. Any other land was scattered as small islands across the global ocean. But since it contained most of the land on Earth, it was technically a supercontinent for the time, even though Ur was most likely smaller than Australia today. Ever since then, Ur has transferred from continent to continent for billions of years. What is left of Ur is split among India, Madagascar, and part of Australia. Colombia. Now we are starting to enter an age where we have slightly more evidence. The continent of Colombia formed 2.5 billion years ago. It's believed that the continent stretched 8,000 miles, or around 13,000 kilometers for you commies, north to south, and 3,000 miles, nearly 5,000 kilometers, east to west, at its widest point. Rodinia. Keep in mind the span of time is vast. Rodinia lasted almost 500 million years. That's the rough equivalent since the beginning of multicell life itself, until now. I can't spend the whole video saying what was where, but to put things into perspective, modern-day North America sat on the equator, Antarctica lay just north of Canada, and Australia north of that. 700 million years ago, Rodinia began to break apart. This breakup wreaked havoc on the Earth's climate, and sent it spiraling into a global ice age known as Snowball Earth. Ice sheets span the entire planet, with the equator resembling modern-day Antarctica. It's believed these harsh conditions delayed multicell life until the glaciation passed. Pangaea. Even though Earth has existed for billions of years by this point and continents have come and gone, all of the land pretty much looked like this. And now we have reached multicell life finally developing in the oceans of ancient Earth. So congrats, life. Only took you a few billion years and 7/8 of the planet's history. Lazy bastard. Pangaea was located almost entirely in the southern hemisphere, hence the name meaning southern land. You could travel south from Canada, down into South America, then just head straight west into Africa, and for the only time in Australia's life, it was on top of everybody. Gondwana. Gondwana was pretty much the central hub for the southern hemisphere lands, Australia, Antarctica, Madagascar, South America, and Africa, before South America decided to run off with that North American scoundrel. Gondwana stretched from the South Pole all the way to the equator. Gondwana saw the rise of arthropods, fish, amphibians, and reptiles in its 300 million year history. Global temperatures were far hotter than today, and so lush forests descended across the continent, even going down to the South Pole. Eventually, Gondwana would combine with another continent to form Pangaea. That continent was Laurasia. Laurasia was the northern counterpart to Gondwana. North America and Eurasia had clashed together, forming the Appalachian Mountains. The animals and plants that died on these mountains eventually became the coal which is mined today in areas like West Virginia. But millions of years ago, the continent Laurasia was divided between a massive Appalachian range, which in their glory days were the size of the Rockies. Laurasia is the simple combination of the two continents' names. Laurentia, the North American Craton, and a better continent name in my opinion, and Eurasia. Pangaea. Eventually the two great continents combined into a supercontinent we all know and love, Pangaea. Pangaea is seen as the genesis for what became our modern continents. When it died, the continents split and made their journey to the world we know today. Pangaea oversaw a catastrophic extinction which wiped out 96% of marine species and 70% of land species. But from this catastrophe came the dinosaurs, who wandered the vast continent. Throughout the age of dinosaurs, Pangaea began to break apart. 200 million years ago, North America and Africa divided apart, and the Atlantic Ocean was born. The northern Atlantic Ocean forming well before the southern. Around 150 million years ago, our good friend Gondwana split apart. Africa and South America split, leaving the distinctive puzzle piece shape we see today. Antarctica, Australia, and India all split apart from one another to become their own continents. 100 million years later, Europe and North America would finally divide, which means even after the death of the dinosaurs, Europe and North America were still one. India combined with Asia 40 million years ago, traveling the Indian Ocean for over 90 million years. In the vast history of Earth, our 7 continents are simply one moment in an endless ever-changing movement. Supercontinents may not exist today, but they will exist in the future. And perhaps future humans or other beings will think it was strange when the Earth wasn't just one continent. In 19